5 to begin again today.
Mm-hmm.
I don't know. Might be a great class again. No.
Yes.
I know 2 people are coming for sure.
Okay. All right. Well, be the late arriving crowd. But, well, we're going to start with, we're just going to get started because this is the most amazing part of the class. We're finally to the structural part of structural equation modeling. So, today's a lot of fun, for the most part. We're going to cover, well, I mean, fun depends on your definition of what fun is. Fun for me, I guess. We're going to get into path analysis first today. And path analysis is a series of simultaneous regression models where some of the outcomes can be predictors as well, but every one of the variables is observed. And then what a structural equation model is, uh-oh, there's Siri again. I don't need you, Siri. Structural equation modeling is the path analysis where one or more of the variables are latent. So you have a measurement model in addition to it. So that's where we're going. Anybody have any questions before we begin? Okay. So the path analysis. When you guys took, everybody took multivariate, did you have multivariate regression?
Multivariate regression?
Yes. And did you do multivariate regression in R?
Mm-hmm.
What package in R did you use for that? LME for? Or NLME.
Yeah.
Okay, good. So Billy used some more of my stuff there. Then you used different types of covariant structures?
Mm.
Yeah? Maybe? Does it remember?
It's been a couple of years.
In a couple of years?
Time, yeah.
No? No covariant structures? Well, maybe not. Anyway, the first type of path analysis you did was that. A multivariate regression, if you're using a linear model package, like LME or LME4, like proc mixed in SAS, what it will do is a regression analysis like you see here, and if we were to depict it, remember our path diagrams that we had before, a square is an observed variable. So here we've got 1, 2, 3, 4 observed variables, right? 2 predictors and 2 outcomes. And this type of path analysis indicates that predictor X or Y1 is being predicted by X1 and X2, and Y2 is being predicted by X1 and X2. So this is the type of setup that you could have done in a regular regression analysis package. Actually, you could do it in, well, you'd have to do it in a mixed model type package itself. You couldn't do regular regression because if you did regular regression, it would not estimate the covariance between the 2 outcomes. Whereas here, that's something we need to have. So the path model is just that. It's a multivariate regression for two or more outcomes simultaneously for the same unit of analysis, so the same person or the same level. And most often this gets expressed as a diagram, and these conventions that you see that you've seen before still hold. Our boxes are observed variables. Our circles are latent variables, or sometimes residuals. And if we have a one-headed arrow, it represents a regression. So here, this arrow starting with x1 terminating with y1 means x1 is predicting y1. And then there's a two-headed arrow that represents an undirected relationship, in this case of covariance. And remember, all of this we've learned about before because we had to do it in certain forms for CFA and IRT, particularly when we translated what we wanted to do with the model into Lavon. Each one of these versions of the picture had an analog in Lavon's syntax, right? So the single-headed arrow in Lavon is just a single tilde. The double-headed arrow is the double tilde, right? What you don't see here, because every variable is observed, is the equal tilde. That is not in this one. But if you added that, if you added a measurement model, it would be there as well. So what's happening here is we're trying to predict the scores of two outcomes, y1 and y2, and we're using x1 and x2 as predictors for both. So it's like having two regression lines that we're going to estimate simultaneously. Now, you may wonder, why can't I just do this separately? Well, you could do it separately, but by doing it simultaneously, when you have a covariance matrix amongst your outcomes, like this right here, talking about the variance of each of y1 and y2, the residual variance in this case, and the covariance between it, what you end up doing is borrowing information across the two. So you sort of allow for more information to take hold in your model itself. So it's a little bit more convenient. Furthermore, if you have, depending on missing data, it may be better or worse to do it this way. So really, this is multivariate regression for past models is like two separate, as I was just saying this, two separate univariate regressions estimated simultaneously, right? You get beta 1 and beta 2 that provide the unique effects of the predictors, right here. You can calculate an R square for y1 and an R square for y2 as well. Right, so it talks about how much are these predictors accounting for variance in each of these. You'll note that the beta effects are different for each of the models, and that's because I hate it when PowerPoint does this. I can't erase. All right, come on, PowerPoint. Doesn't give me what I need to do. There it is. Press and hold. It's not working either. Anyway, I'll calm down. I'll quit getting angry about the software and just get back to the model. You'll see here, the way this gets, I like to sometimes notate this is, this beta coefficient, it's the first beta coefficient predicting y1. That's what that really means. So beta 1 y1 is there. And that's different than beta 1 y2, right? Beta 1 y2 is the first beta coefficient predicting y2. That's what the superscript means. It's sort of what's being predicted, and then the subscript is what's predicting it. So why do we want to do both at once? Well, we can test the difference in size of the coefficients, right? But also we can test for things that we don't necessarily get in a regular regression analysis, although not necessarily in this direct multivariate regression. But if we had a more complicated analysis, we could test for mediation effects, or in this case, in the presence of an indirect effect. Right? So basically, this is saying like a variable like x1 may have a direct effect on y1, but it also may have an indirect effect through other variables on y1 as well. So
what you are saying basically is that you are doing like simultaneous and sequential analysis at the same time.
Simultaneous analysis at the same time, yep.
And sequential?
Sequential I always think is more than one analysis. That's usually where I usually think about it, as like a sequential process, but you may use it differently than I do. So.
What I have in mind, that I'm reading about this, so we like for the simultaneous we will enter all the independent variable, then in one block, then inserts variable by variable or subsequent like blocks.
Right. No, we're not doing that. That's multiple analyses. Right? You're going variable by variable, trying to see whether or not you need to add it or subtract it from the model. Is that what you're saying?
Actually, I'm adding the same variable.
Okay.
Like I put all the variable at once, then I created, like I copy paste the same variable and enter it again to the model as like a block in itself. Then enter again until you get done with the variables to see what's the differences.
Oh, every time you're running a model.
Yes.
No, we're not doing that. That's the difference. Here, one model. You put them all in.
All at once.
Run it once. Whereas you're doing, put one in, check. Put another one in, check. Put another one in, check.
Put all of them simultaneously.
Okay.
In one block. Then create another block, including one variable.
Yeah, I don't think I understand.
A block like SPSS?
Yeah, I'm talking about in terms of using
like partial correlation individually.
Oh, so basically, it's a sequential, like a stepwise regression?
Kind of, yes.
Yeah, so a stepwise regression uses multiple analyses. There's multiple models for it, right? SPSS is ridiculous because it automates it for you. But if I think what you're talking about, like there's a forward selection procedure and a backward selection procedure and all that, is that right?
Yeah, it's kind of. Yeah.
or stepwise, or yeah. What it's doing for you is running one regression after another, and making decisions on what should stay and what should leave from the analysis.
One simple regression.
Right. What we're doing is not that. We're doing one analysis, but we're putting in multiple dependent variables. The other thing in SPSS is I only think you have one dependent variable, right?
Yeah, of course. Yeah.
Yeah. Here in this, you have two. And not only do you have two deep and independent variables, you have them where they are where they're also correlated with each other, residual variance and now the residual covariance between them. So this is a very different analysis than what that is. Right? That makes sense. So that's I get the block thing. I guess I'm blanked on. I spent a long time since I've run SPSS. So that's sort of for those of you who might become quantitative people, or be the person who's relied upon for quant. All of you may be. After this class, all of you will be. The way that you can avoid having people say, help me with SPSS, is say, I don't even have it on my computer.
Oh, nice.
I don't know how to install it. I don't have it.
I just said that last week.
Sorry, I can't help you. That is my go-to default. If someone says, hey, how do I do this in SPSS? I have no clue.
What if, hypothetically, you're teaching a lab that teaches SPSS? What do you answer people?
Then if you're teaching, are you the instructor of record for the lab?
Yeah.
Because you actually have academic freedom. You should say, I'm going to teach this in R.
Oh.
Yeah.
That's difficult. Like
Well, according to the Higher Learning Commission, which is our kind of accrediting body for the university, they expect that supervised graduate teaching assistants, or people who are appointed as instructor of record, even with supervision, should be given the academic freedom to understand what they're doing in class. Now, I do think you have the academic freedom on how you probably present your SPSS.
That's true.
Right? So that's probably where she'd go, and that's legitimate, I think. But no, I would say friends don't let friends use SPSS.
Okay.
Yeah, that's pretty much it. Sorry, I don't typically. Well, I hate a lot of things. I'll just go with it. I hate SPSS. I do, and so yeah, if someone comes to me with SPSS, I'm like, we quit using like the Model T when it went obsolete. Right? I don't know. Maybe has it gotten better over the years? I quit using it in.
It doesn't change ever.
Really?
In my experience, like it's the same.
But even for like data entry though,
Oh, yeah.
against it, I'm
There
just
is,
teasing.
but
So what would
you
you
notice
say
the
is
problem.
like for data
Never
entry?
tried.
We have a lot of like undergrads that do data entry and they use SPSS.
Yeah, I mean Google Sheets would be fine. Anything that would, anything would be fine. You want to keep, actually SPSS has a script-based language too. Anything with a script is nice. Excel, whatever else. But I mean, if you really get into it, if you have a really important project, everything project's important. But if it's like one of these high, like someone's going to sue you if you don't get it right, then you probably want to have your own front end to have people enter data themselves and then have it put it in the database the right way to go. But yeah, there's all sorts of ways you can script data in SPSS, like you can in Google and everything else too. Yeah, but
You can use Python in SPSS.
yeah, you
It's
can use
Python.
Python in SPSS. That's right. Yes, and in Excel, if you're familiar with, I don't know, there's if you Alt F11, there's Visual Basic backend, which is not great either. But I learned that was the first language I learned, Visual Basic. But it's anyway, yeah. Try not to use SPSS.
for me, I am an advocate for R, but
You don't have to say that to get an A in this class. You're going to get an A anyway.
actually,
If I could give you an R, you'd get it.
But I have been working in R just to understand it. It's now maybe 1 year
It's
to
tough.
get acquainted with it.
It's a lot to learn. I still don't know enough R. I don't know if any of you are on the. I have this work group I do in CRMDA, Bayesian statistics, and we're building an R package to do Bayesian analysis. And the latest discussion has been ways of doing things in R. And Paul Johnson over there has been very good about we had this problem that posed. I didn't know how to do it in R, and he keeps solving these problems with it. So there's a lot. Basically, what I'm trying to say is scratching the surface of R. Probably the same thing with SPSS. Here's what my problem with SPSS is. A lot of the things it automates for you is hard to replicate, hard to redo. And then a lot of the times, Jesse, are you teaching syntax for your SPSS?
We cover it very briefly.
And see, that's the problem. So if you go through and click options and so forth, how are you going to replicate an analysis? In the era of replication that we have right now, or in the era of reproducible research, you have to know the exact button pushes that you have, or paste the syntax out, right, every time that you do it. Otherwise, it's gone. Now, most of the users I found don't even bother with it. Now, you can do it. You can certainly do it. But if I really go the nail in the coffin for SPSS, I was doing a mixed model with it several years when I did touch it before. Actually, it wasn't me. I think it was Lisa that was doing this. And we had a logistic regression with a random intercept. She's not overly... It's a complicated model, don't get me wrong, but it's not like path analysis, right? And it runs, it starts to run and does stuff, and then it spits out output. And in the box where the parameter estimates, standard errors, and everything else, every single one of them had a series of question marks. It said it converged. I was like, I'm done. I just don't even want to play around with this anymore. So, anyway. Yes, I shouldn't say we all have our preferences with software, but so long as you can do reproducible research and it does the job that you want it to do, I guess it's okay.
Actually, why I discuss this, because I have an experience building models in SPSS. I start to build my own model through R, like multiple regression. In SPSS, they have different
criteria.
It's to me like it's embedded features in the software program itself. So just you select the options and it will run it for you. But in R, you need to learn.
Yeah, you have to code it yourself. Well, someone may have translated it and done that in R as well, though. There's all sorts of packages. You probably could find a lot of the stuff that does in SPSS. So. I know when I taught multivariate last time, actually last two times, and I'm going to teach it this way in the spring, I had taught it the first couple times I taught it in SAS, because SAS has a good mixed model package. And multivariate to me is effectively a course on mixed models. And then I translated it in R, and I didn't think R would do all this stuff, but sure enough, it did. I just had to find the right packages, had to find the right people have developed it for it. So anyway, yeah, there's knocks on every one of the packages. I shouldn't be so hard on SPSS. But that being said, if anybody wants to see me get upset, just mention parceling or SPSS. Parcel? No. All right. Let's go back to this here. So there's two different types of, just like in regression, there's two different types of solutions for your model. There is this unstandardized solution, right, where your beta weights reflect the scale of the variables that they're on. Right? It's the same thing that happened with what we were doing with CFA. Right? So in a regression model, how do we interpret the intercept? It's the predicted value when x1 and x2 are equal to 0. Right? So it happens to fall on the scale of y, right? It's right there on the y value. What is beta 1? It's the increase in the predicted value for every 1 unit increase in x1. And so beta 1 is on the scale of units of y per units of x, right? So that's your typical deal with regression. But there is a standardized solution. Did you talk about standardized regression slopes in your classes? Okay, that's good. Hooray! Just making sure. The standardized solution in regression works the same way as the standardized solution in factor analysis. Right? We take the units off, right? So if this was standard deviation of y per standard deviation of x, right? Up here, we just have to multiply by standard deviation of x, divide by standard deviation of y, and we get our standardized solution. Right? And the same thing happens in our path model. So these are really good when we compare effects within a solution because they're on the same scale. If you were to look at a path analysis and say x1 and x2 had different standard deviations, then the size of the coefficient for beta 1, actually if y1 and y2 had different, if y1 was something like something that had to do with like age and years, and y2 is something like money, like in thousands of dollars or something like that, like your annual income and like, your age or something like that. I don't know why you'd be predicting age. I don't know if anything is predicting age. Maybe it's something like your GPA and your income, something like that. All right. Because the scale of those units are so big, you could have effectively the same size of coefficient standardized, but beta 1 and beta 2 will look very different because the units that they're predicting, the units of y are so different, discrepant. So, so we use the standardized solution for that. But there are some new and confusing terminology that we use. And this is just part of the fun. If you have a predictor in a model, like x1 or x2, and it's not predicted by anything else, it is called an exogenous variable. Exogenous. Lisa's mnemonic device is the letter X, like predictor. So, x1 and x2 in this example are exogenous. Alternatively, if you're not exogenous, you're something called endogenous, which in this case would be y1 and y2 if you're being predicted. Now there will be a case coming up where we do something like this. X, variable m, variable y. Lou, what is this? X predicts m predicts y? Mediation. Hooray. X is it exogenous or endogenous?
Exogenous.
It is exogenous because there's no arrow that terminates at it. Is y exogenous or endogenous? Endogenous. What about m? So the definition that I go by is if ever you're predicted, you're endogenous, even if you're predicting other things. So m is an endogenous variable because it's predicting other things.
Predicted.
It is a predicted variable. All right. So here, y1 and y2 clearly are, but in path analysis, we'll quickly run into a case where this happens. And by the way, just talking about it, this top model here, you could do with LME or NLME and R, or I don't know what SPSS does. I can't tell you that. I don't have it on my computer. I can't even install it. I don't know what the problem is. This one cannot be done in the typical mixed model package, like NLME. And that's because the endogenous variables that predict other variables, it has no way of accounting for. Yes?
We use single arrow in path analysis, but it doesn't mean causality.
Right, yeah. Same thing that goes before. Causality is... you cannot prove causality in correlational data. Right? Causality is more of a research design, right? So if you were able to, if X was a dummy code for which group that people randomly got assigned to, and you were saying that the group predicted some type of outcome, then you have more of a case to say that the whatever the random assignment process and the treatment that one group would have something to do with the causality. But causality is more of a research design. Shada.
So can you explain one more time why M would be endogenous in that bottom example and not both exogenous and endogenous? And
because when a variable gets predicted by anything, it becomes endogenous. That's sort of the rule for endogenous variables. And I know it's sort of the text up here is sort of the outcomes. What happens for an outcome and a predictor? If ever you're endogenous, you're always endogenous, regardless of how many times you're predicted. That's sort of how it works. So if you are being predicted, if there is an arrow that terminates with you, a unidirectional arrow, right, one-sided, and it ends at the box that you have in your diagram, that variable in the box is endogenous, regardless of how many other things it predicts.
so if you're looking at 3 different variables, then you think that they're probably all have some sort of relationship back and forth, like self-determination, opportunities, and like self-regulation.
Yeah.
Then they would all be endogenous variables because you think that all of them have the ability to predict and our outcomes.
Now, that's the other thing. This type of path analysis that we talk about here, there's a certain shape to it. If you have this X, M, Y, and then you have the double arrow like this.
Mhm.
This is, that's a correlation matrix. It's not really a model itself. And the reason for that is the types of models we're going to deal with are types where if you trace the paths, you can never go back in a cycle. Whereas here, if you trace the path, like if you look at this middle graph, if I start at X, I can either go from M to Y or just to Y, but there's no other mechanism to get me back to X. And the term for that is, we call this a non-recursive model, or a recursive path, a non-recursive path model. So anyway, it's another large term that I never ever use. You can't have a cycle. Another term for it in the more that I am more familiar with in like the computer science literature is this is called a directed acyclic graph, right? So that you have a directed relationship between variables, and there's no cyclic behavior that can happen to go backwards the
One
direction.
way.
That's right, one way only.
So, and I apologize.
No, this is great.
Covered this, but so are the double-headed arrows simply a correlation?
That's it exactly.
Okay.
Covariance, really, but yes, proxy for correlation.
So yeah, without dividing by the standard deviation.
Exactly, yeah.
So then the single-headed arrows, that means that we predicted a variable.
That's right. There's
And that's why we can't go back. We don't have the information to go back. The total information.
that, and just if you think about it this way, this is these variables themselves all represent some type of cross-sectional relationship, right? Now they may have time 1, time 2, time 3, and that might be different. But you may have an X at time 1, a time 2, and time 3, and a Y at time 1, time 2, and time 3, right? So you may have this relationship where this might be X1, this might be X2, and there may be something like this going, right? But for a cross-sectional relation, it's hard to show. Just think philosophically. Now, about causality, right? This model, if it fits, it's plausible that it is a mechanism that's causing it. Now, there's other reasons for what's happening. But in cross-sectional data, like you have one snapshot of data, how can you show that what you're doing is causing something else, or what you're doing is directly making this happen? It's hard to. It's a weakened argument, right? So it's more of a description. And really, what we're going to get from this, and actually, Jesse, this is sort of a big picture mind melt of it. But it's that when we have cross-sectional data, what we're doing is playing with correlations, right? So we have this potential where we put a path diagram on it and it fits well, and we say, and it makes sense, and there's significant paths, and we say this is what's happening. But then someone can come along and draw an equivalent diagram with the same variables and say, but this is what's happening. And it's equally plausible, right? Because it will fit just as well. Right? So it's the idea when I said before, when you have 3 variables to get a factor, and it measures it perfectly. And I say it's equally plausible that 3 things are just correlated rather than you have a factor. Right? It's the same thing that happens in this type of setup, especially with X, M, and Y, which is a very traditional mediation setup, because it could be the case that Y predicts M predicts X, and Y predicts X, right? And that's an equal fitting model to the other. It's just redescribing the covariance matrix between the 3 variables.
So what about switching between X and M? X would be the mediator.
Oh, you could do that too. Yeah, that's also equally likely. Yeah.
The logic is that the explained variance in M by X would be the same of the explained variance in X by M.
And that's not necessarily the case. You may not get the same explained variance, but you get the same model fit. And if you go and look at ultimately here we have 3 variables, and we have a 3 by 3. If we look at the data, we got the covariance matrix from it. Then when we go and fit the model where X predicts M and Y, then we get one version of those. We take those numbers and we come up with the beta coefficients for it, one way. And then if we do the other type of model where Y predicts M and M predicts X, we do another formulation with the same numbers and come up with different beta coefficients. And the result of those beta coefficients aren't likely to be the same. They're likely to tell a different picture, different proportions accounted for, but there's nothing left over to go different ways. It's not like saying, like in an overdetermined solution. Like if we had, what we have when we fit this 3-directional model, it turns out we have a saturated model. And so that means all the information in the covariance matrix gets parsed into the model parameters in one way or the other through a series of linked equations. And that's where the equal plausibility might happen, but it's not equal in terms of size. It's not, in fact, most of the time it isn't at all equal. It means like, oh, look, X explains 50% of M's variance, but M explains 20% of X's. This is actually an outcome that could happen. So
Tuesday you talked about.
Equivalency between models, yes.
Is that what you're talking about?
That's what I'm talking about here
Okay.
too, yes. Actually, the models here are, let's see if I can break out of this here. The models here are, we're sort of explaining equivalent models, right? If we did X predicts M predicts Y, and X predicts Y is equivalent to Y predicts M predicts X, Y predicting X. Right, so these are equivalent models. And by equivalent, how do you know a model is equivalent? It has the same log likelihood in the output and the same number of parameters. Right. So, or degrees of freedom is another way of putting that. Where am I going here?
So then, like in a paper, when somebody says that, you know, this model is like the best fitting model or something like that, and somebody else might review it and say, well, actually, it might go the other way.
That's right. Yeah.
And then what would be your counter argument to that? To say, well, no, theory says that would
you could try to do theory, but again, there's no empirical evidence to suggest that to refute that argument.
So
it's equally plausible. I mean, there are certain things. If you collect X at X, M, and Y, but there are different points in time, right?
Yeah.
You only have three. Like, you know, this is like your high school GPA, your college GPA, and your income at 35, right? Right. So think of it that way, right? You could do X, M, Y, like this first one here. It's hard to see that your income at age 35 explains your college GPA, which explains your high school GPA, right?
Yeah.
So there's a logic that you might be able to argue, like, yeah, that one's true if there's a time machine, right?
Perhaps not for a lot of research, like school-based research, where it's all at once.
That's exactly it. Cross-sectional research, it's there. Alternatively, if you come up with a more complicated model that is more falsifiable, like, again, this mediation model is very, very much it's just identified. It's our saturated model that we would have in a CFA. If you have a fourth variable that you put in there, right? Now you've got a theory that's testable, and not every reconfiguration of it will be the same, right? So there are ways that you can do that. Now, there'll still be equivalent models, but there might be fewer of them, or they might be less realistic, right?
So, what about arguing in terms of the loading, the slope itself? If our purpose is even exploratory or prediction, what do you think about?
Again,
because we have different,
it's just recombinations of the same information to begin with. It's equally plausible. There's really nothing you can do. I mean, particularly on a just identified model, when you come up with an equally probable model, equally likely model, it's just.
But you indicate that the slope will be different for each.
It may be, yeah, it may be. But one of the slopes will be different in one way, one might be different in a different way. Right? So
like the same magnitude, you mean?
I don't know. It's not exact. I mean, you can draw the math out, and you can come up with a system of equations, what each of the betas should be, and what each of the residual variances should be from the covariance matrix of the data. So, again, you do it differently. You switch the equations around, but it's just another input and output. It's, you know, I don't think there's an argument for that either. It's overall the whole thing's one way likely or the other.
So longitudinal data could be used to show the one directional relationship. Then could it be proved?
It's a little. No.
Still no.
Well, a couple things. If you have a research design where you're doing some type of randomized assignment across time, potentially you may have a better argument for it, right? Right. So if you can do that, if you only have correlational data, if you're only observing people at time 1 and at time 2 and at time 3, it's not likely to. You're most likely not going to have a good case against causality. And so the way I look at it this way, people talk about this as a causal model. What are the two things that have to be for causality for me, right? The model has to fit the data. If the model doesn't fit the data, it's not even plausible it's possibly there. If the model does fit the data, then the question is, okay, do you have a research design where you had effectively manipulated the variables to sort of say, my manipulation is the only thing that differed between these variables, right? So for instance, if you're trying to talk about gender differences, or Mayumi, you were talking about differences in status of a student, support status, right? Can you randomly assign a student to that? No. Can you randomly assign someone a gender? Probably not.
No.
Right? Actually, I say probably because I saw there was research that someone did where they allowed kind of a mapping of someone's voice onto another person's. So I could be talking, but an avatar of a different person altogether would be speaking for me. So it could be a woman, it could be, you know, someone from a different race, a different color, whatever. So he was. I think the only reason why he was doing this is he really wanted to randomly assign gender, but or sex or race. He's like, oh, the hell I can. I'm not right. But yeah, the point being, if you really want to talk about causality, you think about just philosophy of science wise, and I'm not a philosopher of science, but my basic understanding of it is to show that something caused something else, you have to make sure that's the only thing possible that changed between the two, you know, between the situations, right? If you're going to say I have this treatment that causes students to do better when they get it, you have to make sure that the students who receive your treatment, that's the random assignment process is important there because you still, in theory, the groups should be roughly equivalent going in, and the only difference between them when going forward is that some sets got their treatment and some set didn't, right? So it's really hard to do.
Confounding variables.
Yeah, and plus there could be confounding variables as well, even with random assignment, right? Particularly over time.
I think in single subject research, it's like threats to validity.
Yeah, that's exactly
So what
it.
are threats like maturation and history and exposure and contamination?
And that's exactly the same deal here. It's all the things that would be threats to validity are threats to the idea of causality in the study, including equivalent models also, right? So these are all things that you have to think about. And again, you don't want to get sold, like, I love statistics, but statistics can't prove everything in the world. I love math. It's not possible to eliminate all the things that go into a system, particularly as complex as the universe that we live in, the world that we live in, right? Or even make it even smaller, like create a little world. I'm thinking like a little gerbil colony or an ant colony and do research on it. You can't control everything that's going on, right? So it's something that you do the best you can, but know that you have to really, to not oversell the research, which I think is important, is to understand its limitations. And in the path analysis world, no, it's not causal unless you have the design that says so. And even then, you still have some certain threats that might, depending on how it was collected and how things work.
But as long as you state, you can say
Yes.
that like the model suggests a causal relationship. However, there are limitations
Right.
that should be acknowledged.
Yeah, I believe probably staying away from the causal is a good idea. Just to say, this is the model that we believe is an accurate representation of what's happening. You're sort of implying it, but I think causal is such a buzzword. Like, when can you? It's almost like the word prove. I proved this. Well, there's one field in our social sciences that, but I guess it's in the College of Liberal Arts and Finance. There's one that you can prove things, right? Actually, two, right? Philosophy and then mathematics, right? In those cases, you can demonstrate proof, but in most of the cases for empirical research, it's like saying, "I prove this." I didn't really prove it. It suggests it's a softening of it. I mean, and the thing is, evidence can be then it becomes an accumulation of evidence issue, and it becomes corroboration of other studies and all this stuff. It's just the typical type of research process that you do to try to understand what's happening, but trying to narrow down all the things that could also not happen as well. Replication being part of it, absolutely, yeah. So but just I'm telling you this more the caution. I think, I learned about path analysis. I thought, oh, this is great. I remember being an undergraduate in one of my classes, and my professor was talking about, oh yeah, there are people it was like a research design / statistics class, and the professor was saying, well, there's these new methods that are coming out that are like path analysis that, they think they can do causality with correlated data. So people like that aren't into the field or think this. And it's like, well, you have to take care to say, well, it's tough because you want people to listen to you. And if you believe the result, you want to share that result with the world, but you also have to not do it in a way that exaggerates it, I think. But anyway, it's a tough trade-off. I would, I guess my own personal, this is just me, so choose how you want. And if I say, I try to avoid the word causal at all in anything I say about it, particularly for observational research or even experimental research where there's not a whole lot of control, quasi-experimental or so forth. So, so I do, I use everything but the word causality. Strongly suggests, or a process or something like that, but it's, yeah. Okay, sorry, I'm going off the rails a little bit. So here in the top we have our previous example. We have the x and y being what are exogenous. X is. What is y? Y is endogenous. But now if we end up having this right here, we add another regression slope to it. This is what I was saying. Y1 is being predicted and it predicts Y2. So it's anytime you're predicted, it's your endogenous. Just remember, anytime there's an arrow that terminates, endogenous. The terminology exogenous, endogenous goes back in time. I mean, it's like 1920s or before. I want to say its roots are in econometrics or econ somewhere. And that's fine. It's great. I think in my understanding of it, like it matters less when you're using path analysis as a practitioner. Like if you're trying to use this to take your data and analyze, you don't necessarily need to know what's exogenous and endogenous anymore because software will take care of it for you. But from the mathematical point of view, and Lou can come up there and tell you this, right? The exogenous and endogenous, if you talk about the likelihood function and write it out, then you've got a set of matrices for exogenous things and another set of them for endogenous things, and that puts together the function in a certain way because each of these builds into portions of the covariance matrix, just like factor analysis does. So because of that, I think you hear this a lot, but realistically, it's not that big of a deal. The one catch being anything that has an arrow to it, anything that's an outcome, you would expect to find an R-square for. Right, that's it. That's the big thing, I think. Can you think of anything else, Luke, that I missed on that? Yeah, that's about it? Okay. Sweet. All right, so the other part that's a little bit touchy is that when you estimate parameters for exogenous variables, the different programs that you might use treat them differently sometimes. So in a regression analysis, when you say y equals beta 0 plus beta 1 x plus error, what assumptions do we make in a typical regression?
The linear dependence, random residual.
That's right. Our residual is normal, the mean of 0, the variance of sigma squared or sigma squared error. What assumptions do we make about x?
No, let's stick with it.
No.
The dependent.
The deep y, consequentially, because of this, x is considered a constant, right? With no assumption about its distribution. It's observed. I wouldn't say it's a constant. It's a variable. Sorry, it's observed. It's not a random quantity. Not only that, we say that x is perfectly reliable. That's the other term, right? That's sort of what this class is about. But yeah, so x we've observed. That's it. All right. And what we're doing with this regression model is really we're saying the distribution of y conditional on x follows a normal distribution where the mean of that is given by beta 0 plus beta 1 x, and the variance is sigma squared error. Right? That's what we're saying. So the y is not normally distributed necessarily, but the distribution of y given x is. Right? So how to think about that? If x was a 0 or a 1 variable, right? This is effectively a t-test, a two-group ANOVA, sorry, one-way ANOVA. Right? And if you have a really big effect size, what this model says that you should have is this distribution for y. This is y, right? And this might be when x equals 1, and this might be when x equals 0, right? So if you were to erase the x's down here and just look at y, you'd have this double hump camel. And that's a good thing. That's your effect happening there. So, but that's not a normal distribution for y, right? It's only once you understand the mean, once you condition around the mean, if we were to lay these two distributions right on top of each other where the mean of it is, what's left over, or error then, has that normal distribution. So why I'm saying this to you is Levon takes x and puts it as part of the estimation process in the likelihood function. And so you end up having x with a normal distribution when you use Levon, the assumptions of normal distribution. M plus does not by default, although you can make it to be part of the distribution. So if you were to estimate a regression, for instance, right here, x is not part of the likelihood process of estimation. Even in a mixed model regression, x is not part of the assumptions that are used. It's just x. So the ramifications for that are not large, because the normal distribution doesn't necessarily change a whole lot of things. Where it starts to be a big issue is if you have missing data, if you're missing some of the predictors. If you assume they're normally distributed, it's going to use a normal distribution effectively to sort of skip over them. But it's not that, again, not that big of a difference. So anyway, M plus, if you're worried about that, M plus is the way to go. I think I would really wish Levon didn't do this. I like not assuming normality of x. But by the way, this is where you start to get some of the historical issues in text that you might have read about SEM. So Rex Klein has a book. I don't know if the new version of it is different. The older version of Rex Klein, the edition 2, would say structural equation modeling has to have normally distributed variables. All your outcomes have to be normally distributed. Well, no, they actually don't, for a number of reasons, right? We saw in IRT we could have outcomes that were not, items that were not normally distributed. And also here, our predictors, you don't have to have, there's no assumption about those. But you'll read that in SEM books. Things have to be normal. And that's because up until fairly recently, the software all assumed they were normal and put it as to be part of the likelihood function. So, yeah, Jesse.
You've exposed how little I've understood this concept. But so if you're saying that x doesn't have to be normally distributed, and if the marginal distribution of y doesn't have to be normally distributed, then are we saying that the joint distribution of y and x also doesn't have to be normally, like, bivariate?
Oh, that's a good question. Yeah, it shouldn't have to be. Yeah.
Okay. But once we condition
Yeah, all we're
x
yeah.
conditional y
Yeah, all we're saying is y given x
is
is normal,
interesting.
right? And if you're this is the joint. If you're going with the joint distribution, f of y comma x
Right.
is f of y given x times f of x, right?
Right. Or another way to say that, our f of y given x is the joint divided by the distribution of x.
That's right. Mm-hmm.
Right. Interesting.
Yeah. So that's the, and so it's sort of an interesting byproduct of it, but it's one way that it's actually, if you have non-normal data, this is probably more for just the people who study statistics than everybody else, but if you have non-normal data and you're trying to describe a joint distribution of something that's, let's say, categorical and something that's continuous, a good way to do that is through this product right here, right? You sort of break down the joint distribution into a series of conditionals and marginals, and that starts to make it a little bit easier to describe.
So the margin, the conditional would be the distribution of y given x,
Mm-hmm.
and the marginal will be
F of x itself. That's right.
x itself.
Yep. But on that note, you're going off to learn statistics now, so enjoy.
Generating functions again.
Anyone ever heard of a moment generating function?
I hear that.
Clearly, it's a function that generates moments.
Apparently, we can use that to solve for probability problems when the integral of the actual PDF isn't integrated.
There you go. Ta-da! Proof.
Yeah, I'm sure Dr. Duncan could prove it. I still wouldn't understand.
Yeah.
Thank you.
No, take care. All right, so here's what's going to go on. What goes into the model itself? We observe the mean, the observed variance, the observed covariance. And what comes out is the intercept, which is effectively gives us a value of the mean, very much like we saw in factor analysis, right? The residual variance talks about the residual variance, or the variance of each variable is described by the residual variance, and the regression path talks about the covariance. So once again, if you have a big, long path analysis model, the same logic that applied to factor analysis applies to path analysis, in that if you think this model is the truth, right, then the data should look like what the model thinks it should, and it will reconfigure, and I'm not giving the matrix products, although if you go to my last time I taught SEM, when Lou was in the class, there's a lot of matrix algebra there, but there's a crazy looking matrix form for what it's predicting about what the covariance matrix should be based on the path equations. You don't have to get into it. It's way too complex to like really see the weeds from. If you're going to do some type of dissertation or otherwise, I can point you to a couple books that you can read on it. But the bigger picture is, remember in factor analysis, we say if you think this factor, if there's a one factor solution, your covariance matrix should look like this. Now we're saying in path analysis, if you think this path diagram that you've set up is true, then your data should look like it. Now that it's a lot more complex as to what they should look like, but it's the same process. And the same thing goes for model fit then, right? If you think your data looks like this, you estimate your data, you compare the model fit to of your data, what your data predicts the covariance matrix to be, to what the model thinks the covariance should be, and you derive the same model fit statistics we did in CFA, RMSEA, CFI, TLI, all the stuff that came out before. Does that sound familiar?
Mm-hmm.
Cool. What about identification? Identification. It's a tough topic. It's a little bit tougher in path analysis. And that's because we have an additional concern that we didn't have as much in factor analysis. But think of it this way. Identification. In factor analysis, we had multiple types. We had to identify the factor, the scale of the factor, right? We had to set the mean and the variance. Well, in a true path analysis where there's nothing latent, where everything is observed, they all have their own scale, they all have their own mean, their own variance. We don't have to worry about that type of identification. But we do have to worry about having too many parameters to be able to estimate. And once again, the key to everything is the saturated model, right? If you have an analysis in Levon where you have these four, these four variables, x1, x2, y1, and y2, they're all observed. Sorry, my boxes aren't that great. But you have the same multivariate regression here that we saw before, right? And then double-headed arrow there, right? x1 and x2 are exogenous, y1 and y2 are endogenous. So in Levon, because x1 and x2 are part of the model likelihood, all four variables are part of the likelihood. So you use, there are four variables here. So what's the number of variances in the covariance, or variances and covariances in the covariance matrix that are unique? 4 times 5 divided by 2. So it would be 10 variances and covariances. And then 4 means, right? So this is sort of what you have to, the first step to understanding whether a model is identified. You cannot have more beta weights, regression slopes, plus residual variances than 10. And you can't have more intercepts than 4. Yes.
Isn't the possible degrees of freedom 14?
Yes, 14. Yeah, sorry, 10 plus 4. That's right. So you can't have more than 14 parameters in your model. But it's a little bit more complicated than that, in that 4 of those cover intercepts only, right? This is like beta 0. And 10 of those cover variances and betas, right? Regression slopes. And I guess also covariances, right? So remember which side of the model each of the things work on. The intercepts go for the means, and pretty much everything else go for the variances and covariances. So just like in factor analysis, there's 3 identification scenarios. There's under-identified, where you have negative degrees of freedom. Too many model parameters. Right? That is not good.
But you can't run it now, can you? I did try it. It says no.
Okay, good. Depends on who programmed it. But that's not good. Just identified is when your model fits as well as the saturated model, 0 degrees of freedom. And over-identified, which where you have the number of estimated parameters is less than the number of possible parameters in the saturated model. So therefore, you have positive degrees of freedom.
So m plus output and whatever m plus gives us to Lavans,
Mm-hmm.
they'll be different, or like how much it's going to be different.
It's going to be different depending on how you treat the predictors. In Lavaan, just like in factor analysis, when you put the predictor in a factor analysis, the factor was the predictor of the variables. And so under the intercepts part, you saw the name of the factor at the bottom. So in Lavaan, you'll see the name of the predictor at the bottom of the intercept, and that number that comes out is the mean of the predictor. The same thing under variances. In Lavaan, the variance of the predictor will show up there. Whereas in M+, by default, you won't see that in the intercepts or means section. You won't see the predictors there. And you won't see the others. And you also will see a different reporting of degrees of freedom. You'll see a different reporting of log likelihood as well, because these variables aren't part of the likelihood. In M+, this model would have, by default again, would have two variables in the likelihood function. And so that's where it would end up having its information come from.
Who's accurate? Who's
Yeah,
more
yeah.
accurate?
Well, I like M+ a little bit better because you don't put assumptions on X. But the world tends to do what Lavaan does. So I'm trying to teach you in an agnostic way that it's somewhat okay. But just be prepared for it, how it works.
So there is no other package that can ignore the assumption of X's in R?
I'm not aware of one. That doesn't mean it doesn't exist. So there may be one. I have not looked for one. So, in my quest to try to keep course as streamlined as possible, Lavaan I was trying to stay with. So just note though, if you run this model, this model in M+ versus this model in Lavaan, the numbers actually will look very similar, like the beta weights and everything will look very close to the same. It's the stuff at the top, the degrees of freedom, the log likelihood, they're going to be a little bit different. Okay. And that's the other thing for it. Like, most of the time, the normality assumption on X isn't going to cause you any grief. Most of the time. It's only when some really egregious cases of X not being normal, like if X is a dummy-coded predictor. But even then, it doesn't seem to change a whole lot. Now, I'm not as up on it because I have not studied the math on this, so I don't know exactly. Let me just... Truth in advertising, again, I'm not trying to oversell my knowledge. So I don't know what's happening, but in my anecdotal playing around with it, I haven't seen a big difference to the parameters you're really interested in, and that's the regression weights right here. I don't see those being widely different when X is part of the likelihood, when X is not, when you don't have any missing data, or have very little missing data. Where the bigger issue comes in is if you have missing data, if X is not part of the likelihood function, then anybody missing any X is gone or out. They throw the entire data frame out. The data that data for that person it's list, what we call list-wise deleted. The whole person disappears. Whereas if it's part of the likelihood function, it can be missing and just sort of get skipped over in the process of estimation. And so that's where discrepancies might be found.
So we need to ensure that the data is not missing. And ask, is there missing data for the results?
Yeah, I think that's part of it. They sort of have to be doing that anyway. Missing data is always a problem. So, all right. So the other part of so here's three examples right here. All three of these models have the same number of degrees of freedom. Right. So here we have three variables. Right. Three paths, and then two undirected paths themselves. These are equivalent models that have 0 degrees of freedom, right? So what is the difference between these two? In these models, these are indistinguishable. Whatever. It's writing forever. I probably could have spelled that correctly, but these two, you're like, huh? Right? Whereas because there's 1 degree of freedom here, these are testable. Right? You can test the difference. Actually, pardon me. They're not testable. They're equivalent. What am I saying? Never mind. Never mind. This model right here is not going to work. Y1 predicting Y2 and Y2 simultaneously predicting Y1.
Correlation.
Yeah, it should be a correlation. You have only one correlation between the two, but you're trying to get two paths out of that one correlation, which is not advisable. There is one more catch with model identification. It is possible to build a path diagram, although it's not in these slides, where you have what we call local under-identification. So different parts of the path diagram itself may be misspecified. And what I mean by that is, so think of this. This is one degree of freedom left over. But if I put a path from Y2 to Y1 simultaneous, if I did this thing right here up on this model, we have 0 degrees of freedom for it. Right? So by degrees of freedom only, we should say we're just identified. But because in this section of the path diagram and the path model, we have this relationship that shouldn't be allowed. For that one little small section, it's under-identified for the entire covariance matrix. So technically speaking, there's another definition of where you need to worry about. Generally, there's you can read path model text that give you the matrix algebra. There's a matrix equation you can do to figure this out, or you can do what I do, which is make sure there's no recursive or any type of cyclicity in your path diagram. If it's directional, all directional the right way, it's fine. It will meet that identification condition. Ironically, I tried to give this example when I taught from M+. When did I teach the class? I guess it was 2013 in Nebraska. I taught in M+. And I tried to give this example, and it estimated this model. It actually did. But the regression slope for Y2 predicting Y1 was like 13 million. And the regression slope for Y1 predicting Y2 was like 0.02. Right? I'm kind of thinking that's probably not good, right? Or I wouldn't say 13 million. It's like, 200,000 with a variance of 600, or, almost too much to actually say. It was just a nightmare. So I don't think it actually does that anymore, but I tried to show it in one of my examples. So once again, how do we check a model? The same steps that you're used to in a CFA. Check the absolute model fit. What does that come from? The chi-square, like the overall test of model fit, the RMSEA, CFI, the TLI, all the things we looked at before, that same logic applies. The same process applies. If the model doesn't fit, figure out parts of the model that are causing the misfit, the localized model strain. And how did we fix it in CFA? We looked at normalized residuals, and we looked at modification indices. And sure enough, look at the same. So the good news is, this process of getting a model to fit is the same. Cool? Mm-hmm. Finally, a good fitting model doesn't necessarily mean a meaningful model. Mm-hmm. Right? Model fit is a necessary but not sufficient condition for a good result, right? Remember the classic example of a good fitting model that has nothing to talk about is a covariance matrix that has 0 covariance in all of it. Because all the beta weights should be 0. But the model will fit perfectly. Just you have nothing significant. So what do you need to do after your model fits? Then you can talk about looking at effect sizes, model significance, R squared, all the things that you would do to see if things mean what you want it to help with your hypotheses that you built for your model. So, and here's an example of excellent model fit but absolutely no meaning. You could have regression slopes that are virtually 0. So.
Just a question.
Yes.
Derek, but in regression, I have come across it's also in math analysis, but I have come across the idea that in social sciences, the explained variance, the maximum common explained variance will be 50%.
Yeah, it's not a lot. Yeah.
Not this, and you can explain by many variables.
Mm-hmm. Mm-hmm. Same thing here.
So same logic here.
Absolutely.
Maybe you can explain by this like 30.
If you're lucky.
if
Anybody
I'm
have
lucky.
those of you who play with your data or your lab's data, what are your R-squareds like, and what do you do? What you do? Anybody? I used to have this joke where when I used to teach regression, I had like the R-square Hall of Fame.
Mm-hmm.
If anybody has an R-square that's like, if you think you want to submit a candidate to the Hall of Fame, let me see your R-square. Like the highest I think I ever got was like 50%. Most of the time it was something like 10%.
Yeah.
It's very low for a lot of the social sciences. Now that again, varies by discipline. It varies by how much control over the observations, the phenomenon that you're studying, all the things that go into it.
Questions about it.
But social sciences, because it's because there's so much going on in social sciences that aren't accounted for by the research, it's very hard to explain a lot of the variance.
Cohen published like a paper like maybe in the 1990s or something. In his experience, like because he's a statistician and well-known figure, so he said that the most probable number of variables that would be included, like in regression analysis, would range like from 5 to 7 to 8.
That's usually what happens, yeah.
So there is no more than that. So
it's a typical study, I think, yeah. But,
That's why when I see R squared like 12%.
yeah.
Can I even report this like 12%?
Yeah, I know, it's a lot,
but
right?
It is, I guess.
But it's relative to field. And the thing, the hard part with that is when you look at the regression textbooks, the R-squares are like 0.8, 0.9. Really not reality. So
you say this is excellent fit because it totals one.
Well, effectively, these are like zero. These are essentially zero. So what this is telling us, there's zero correlation between x1 and y1, x2 and y2, and basically zero correlation in all that part of the model itself. Who wants to talk about mediation?
No.
How many of you love mediation? Just asking. No? Yeah. There's some people who are like, yeah, mediation. I'm serious. Like, I never got it in grad school. And like, again, Lou knows this story because the circle of people I surround myself with, starting with my spouse, but then just friend-wise, everybody's like, I don't get it. Mediation is like regression with better marketing, right? It's mediation. Great. And partly again is because if you have this traditional mediational type design, if you have cross-sectional data, it's hard to imagine the mediation process happening instantaneously to produce this, right? It seems sort of odd.
When you say like cross-sectional, because I'm thinking about like my dissertation topic, my department life. It's kind of longitudinal and cross-sectional, and at what time it's complicated. Right?
Yes.
So how we can account for all these? Like it's like
you need a good model, maybe.
like do we try to create different variables to account for these different, like for the time, for the
You may have to. It all depends on what the research design is. I can't tell you directly because I haven't seen it. But yeah, you may have to, depending on what you do, you may have to have time components. You may have to have longitudinal analysis embedded with it as well.
Because I'm not confusing. I'm not sure, but because I'm in the beginning of reading about this, so I haven't got enough knowledge. So, what's the structure equation modeling? It's kind of multi-level modeling, or there is a huge differences between the two?
There are not huge differences between the two. And they sort of get blended. There's even multi-level structural equation modeling, right, which sort of try to put both together. So there's really not that big of a difference between the two. But yeah, if you want to talk more about design, we can talk outside of class, and maybe I can help you with that. But it's hard to tell you exactly without looking at it. And even if I look at it, it still can be very complicated. Well, let's talk about mediation. Mediation is where you think X causes M and M causes Y, right? So M, this is the mediating variable. And what do we mean by mediation? Well, this effect of X on Y, that's called the direct effect. right? Which is effectively what we thought of all of our regression models as having. So you think about it, this is like a beta slope. As x goes up 1, y changes by beta, right? Directly. But here, the mediator has 2 betas, right? If this mediating variable legitimately mediates the relationship of x and y, what that's saying is x actually has an indirect relationship on y. And how is that? Well, that's because as x goes up, let's say goes up 1 unit, m goes up beta m. But as m goes up beta m, y goes up beta y. Right? So how much does y go up due to x on this relationship of beta m? I just said it, right? Beta y is the change in y per unit change of m. But if m only goes up beta m, then the product of those 2 terms is what we call the indirect effect of y, of x on y. Yeah.
So I've seen mediation models like talked about, at least in our work, like if you are in a segregated classroom, then you're going to have less opportunities, and then that's going to affect your self-determination.
Okay.
So I understand that part of it. I guess I get confused with how that relates to like the moderator part. But maybe
Oh yeah, well that's sort of it. Mediation is not moderation.
Yeah.
Although there was I don't know if it still does it, IES, the Institute for Education Sciences, and they put out their call for proposals starting, I don't know, must have been 2010 or so. They had this sort of guidelines for proposals, and one of the bullets was you need to discuss mediation and moderation, as if they were the same thing.
They still have the same thing. It's still a section, mediating and moderating variables, and you have to discuss them in the same paragraph.
And it's funny because that sort of forces a lot of investigators to say, well, we'll look for mediation and moderation, when really they're not the same thing. So a mediator variable is a variable that's completely separate. A moderating variable is an interaction, right? And so if you were to say that what happens is this picture of moderation or mediation this is not anything. Really what's happening in moderation is that you say x predicts y, m predicts y, but also the product of x and m predicts y. Right? So if you have, what was the example you had? Segregated classroom.
Segregated classroom, opportunities, self-determination.
All right, so this is self-determination is equal to beta 0 plus beta 1 opportunities, beta 2 segregated classroom, and then beta 3, which would be the O times segregated classroom. So what that's saying is beta 3 effectively is the change in the slope for the opportunities, well, for whatever the dummy code for segregated classroom is. So if it was a 1 for segregated classroom, this would be how much the slope for opportunity changed if you were in a segregated classroom.
So if you were testing this, you wanted to understand whether opportunities was going to be a moderating variable or a mediating variable, then you would would you try either of them?
No, I think that's more of a philosophical deal. Like there's specific hypotheses that would come from it. In this case, I cannot see how. I can see that, right? Well, I can actually see an argument for both, right? You'd say, well, what is there's a different slope for you're worried about whether opportunity differentially impacts self-determination, right? So in the opportunity self-determination relationship is one way in segregated classrooms and one way when it's not. That's a moderator, right? If opportunity somehow but see the hard part philosophically is I don't see how you can have opportunity predict a segregated classroom.
Yeah.
Right? I guess you could do the opposite. Segregated classroom could predict opportunity, but then you're talking about the difference in yeah. So anyway, it's a philosophical research hypothesis more than it is seeing if it's a mediator or a moderator.
Okay.
So
you would decide that before.
Yes.
Okay.
Yeah. Or if you're like most people, decide it after.
So there is moderation here. Like we would ignore if it's statistically significant. We would ignore the main effect.
No, we would never ignore a main effect. And we'll talk more about that next time.
Okay.
All right. No, and actually, here's why. The moderator, the reason why moderator is the name, is the interaction modifies the main effect. The main effect is an anchor when the interaction is 0.
Oh.
Right?
Name effect what?
Right? The moderator modifies the value of the main effect. And that's,
I call it a simple method.
what's that?
Simple method.
The simple main, that's right. You tell us, Jihong, you were in, I know why you're saying that, because you're in Lou's tell you too. You're in Lisa's class, right? Here, I'll just go a little. I know. Look at this regression equation right here. If SC was equal to 1, then the slope for O is beta 1 O plus beta 3 O, right? Or another way of putting it is beta 1 plus beta 3 times O. And if the slope was 0, if SC was 0, then it's just beta 1. And so why I was saying it modifies the main effect is these main effects are called quote-unquote simple main effects, meaning that the interacting variable is set to a value of 0, and that's what that main effect would be at a value of 0 for the other variable. But really what's happening is the moderation model, because it literally goes and adds a slope to that original slope, or that main effect, it augments the main effect. It's modifying the main effect itself. So it's a misconception. A lot of times in our linear model classes, even when I didn't understand this well, I taught it this way also. But forget the main effects. You can't really describe them. No, that's not true. They're very specific main effects, but we actually want to describe them even more in a mediation, our moderation model. So
Okay.
I'll leave that there. Thanks, everybody. Sorry to keep you.
Oh, thank you.
No, thank you.